It's my pleasure to be the herald for Dr. Michel Kornegay from Morgan State University. This is an accomplished technical woman who has no problem being the first in many areas, especially in her field. She's the first of her family, first generation, to engaged in the technical field of science and engineering, as well as being Morgan State's first PhD, female PhD, that is. As and in addition, she just told us that this indeed was her first virtual technical presentation to such a large audience this year, and we're very pleased to offer that for her. But we told her that even though this is the first for her and she has no problems being in the lead, this is one of many engagements that we're going to have with her moving forward. Currently, she is the director as well as a professor at Morgan State, but the director of the advanced RF and microwave measurement for measurement and electronic design. ARMED is the name that they have for their lab there at Morgan State. So without further ado, I'm going to turn it over to my colleague, Amr. He and I, we are the co-founders for Black Excellence Matter, and he'll give you a little bit more information on the accomplishment that this talented female has given to the field of engineering. Thank you, Amr.
Thank you, Keith. Really excited to introduce Dr. Kornegay from Morgan State. She is also 1 out of 4 Black females in microwave in the nation. So that's another addition to what Keith mentioned. And her research talks about, she'll talk about her research. And I think that will bring light to the depth and the areas that Morgan is working on related to 5G, 6G, terahertz, and relationships with our potential customers, such as the Army Lab and also NASA. So there's deep ties in the East Coast with DoD, and that's what fuels the research engine at Morgan. So what we're hoping here is to bridge that all the way to the West Coast, to Tektronix. And just a little about Morgan. Morgan produces the most number of Black engineers in Maryland and the 4th in the nation. And it is a HBCU, which is a historically Black college university, and the only HBCU that has a program in RF and microwave. With that, I want to pass it to Dr. Kornegay. We're all here to hear from you, and we're eager. Thank you for being here.
Thank you, Amir. Thank you so much. Thank you all at Tektronix for just having this great event today. It truly is an honor to be here, to be with you, just to share a bit about what we're doing in our laboratory as it relates to research, and to also share with you some of the experience in terms of growing the research and being able to go from where I was in terms of being an immigrant daughter to being a professor in such a highly technical field. And so truly thanks to everyone for hosting this talk today. I'm going to share my screen. So again, thank you again for the invitation to speak at the Women in Tech Talk today. Thank you, Selu. We just had a great conversation with your president, Tammy Newcomb. Great conversation. It's just so wonderful to see the level of commitment and excitement that she has as it relates to creating a diverse and inclusive environment for Tektronix. I just want to say that this Tech Talk is a great forum for women. This is an exciting time for women. There's just a lot of activity around promoting and engaging women and young girls in STEM areas. And like I mentioned already, I am just honored to be here with you today. So for my talk, I'm going to be talking about what we're doing in the research lab, ARMED. ARMED stands for the Advanced RF Microwave Measurement and Electronic Design Laboratory. And we're going to talk a little bit about the ARMED electronics research. But before we begin talking, I'm just going to give you a little background about myself. I am an alum of Morgan State University. I graduated with a Bachelor's of Science in Electrical Engineering from Morgan. I went on to the Pennsylvania State University to obtain my master's degree in electrical engineering. And then I actually came back to Morgan to obtain my doctorate degree in engineering. And then from there, I went on to pursue a postdoc at Johns Hopkins University Applied Physics Lab. And one of the things I can say about my journey, my personal journey, is that I didn't do it by myself. There was quite a bit of support, a lot of support, particularly from Morgan State University. They just did an awesome job, and they still do today. They just do a great job of just creating an environment to make students feel that, hey, you can do this. At the time when I was going through, there weren't a lot of engineers, particularly electrical engineers that looked like me, but I still had the support of faculty and family and friends to say, hey, it can be done, you can do this. And so for those who are out there, if you feel that you're the minority, don't pay any attention to that, just know that you can do that, you can do it. So like Obama said, or former President Obama said, he said, yes, we can. So I'm saying the same thing to you today. Yes, you can. And I did. And so with that, let's move forward in our talk today. So this is the presentation outline. I'm going to share with you the ARMED Center overview, our history, our vision, our goals, share with you what we're doing, our capabilities, and some of the research projects that we have going on. And then I also have another slide at the end that talks about how we go about investing in our students. So in terms of the ARMED interview overview, the goal is that we want to pursue and develop innovative communication systems research where we do high frequency circuit and device modeling. We look at measurement and characterization techniques. We look at the design of static and tunable high frequency, high performance circuits. And we are moving towards doing more system level types of architecting and specifications. And most recently, we have been doing signal characterization, particularly as it relates to securing IoT devices, how to properly identify devices as they enter and leave the network. Our facilities and faculty experience offer unique capabilities to help support the needs of our sponsors, to help to provide solutions to challenges in applied research, to develop advanced electronic components and systems, and to look at the development of spectrum efficient technologies for wireless communication and electronic warfare. Our mission in ARMED is to pursue new technologies, solve those hard problems, and secure vulnerabilities in embedded systems for wireless communications. We look at wireless systems that operate from RF to the sub-terahertz frequency spectrum. And the idea is to be able to impact the body of knowledge by producing publications, intellectual property, through the applied research activities that we have going on in the lab. In terms of our vision, we have a fourfold vision where we're looking at developing innovative technologies for next generation wireless communications. As you notice, over the past 2-3 decades, we've gone through a mobile evolution as it relates to technology. We've went from 1G to 2G to 3G to 4G, and now we're in 5G communications. And with that transition comes the development and the proliferation of new capabilities, higher performance requirements for our communications. The next part of our vision is to foster strategic partnerships and collaborations with academia, industry, and government. And a strategic partnership that we have today is with Tektronix. And so we're just so, again, just excited about the partnership that we're starting with Tektronix. One of the things that I do want to disclaim, put out a disclaimer here, is that often when folks consider HBCUs, they consider HBCUs as just a teaching institution. But one of the things that I do want to dispel for our audience today is that HBCUs are doing awesome research, and Morgan State is doing awesome research. And so we are moving forward in establishing long-term strategic partnerships. And it's through these partnerships that we're able to cultivate talent. It's through these partnerships that we're able to grow and enhance our capabilities. It is through these partnerships that we're able to expand our network at our institution. The next, as it relates to our armed vision, is being a leader. Being a leader in terms of our participation in conferences, symposia, and technical communities. One of the things about Morgan State is that I was sharing with the team earlier was that we've just recently received our R2 designation. And so the transition for Morgan State from being a predominantly teaching institution to a research institution has already begun. Our president, David Wilson, is leading the charge as it relates to us really pushing the envelope of being the preeminent urban research institution within the state of Maryland. And lastly, on our armed vision is to motivate. Again, one of the things that Morgan State does well is training, developing, working with students, creating that next generation of researchers and skilled workforce in wireless communication electronics. Now, Amr had mentioned that I was 1 out of 4 females in RF engineering, but I have to correct him. There was recently added 2 more, which were my doctorate students who graduated. One graduated in 2012 and another graduated in 2020. So we have 2 more added to the pipeline, added to the pool, and those 2 came from Morgan State University. Next, I want to share is the Armed Lab Historic Timeline. Now, as I had mentioned earlier, before the lab was known as Armed, it really was just a concept. And this concept was conceived by Dr. Carl White, who just worked with students. He worked with students in the lab. He got them exposed to different RF microwave circuit simulation tools, and he started engaging them on senior projects, promoting using these tools to look at different types of microwave problems. This was back in 1987. In 1997, that's when we officially created or started the ComStar research program. ComStar at the time, ComStar stood for the Center of Microwave, Satellite, and RF Engineering. It actually is the oldest research center within the School of Engineering. And in 1998, it was able to graduate its first set of Masters of Engineering graduates. So in 1996, we had our first cohort of graduate students to enter the program. In 1998, I actually became a part of the first cohort of students for our doctoral program. So we're relatively new as it relates to a graduate program, but we've made some tremendous strides in terms of where we are today. In 1999, we were able to implement the first neural network model implementation in the CAD tool. And then we're able to graduate our first doctorate out of the center in 2001. And of course, the first female, yours truly, in 2003. And then when we looked at our history, the foundation was starting to use the simulation tools. And with that, because Dr. Carl White had a strong background in solid state physics and devices, we did a lot of device modeling, high frequency device modeling, using different types of modeling techniques to model 3-5 devices, semiconductor devices. As we moved on through this timeline here, you'll see that as we reached the first decade within the 2000s, that we started moving from looking at just the device. Now we're expanding to start looking at circuits. So in 2010, we had doctorate students to do work on different types of circuits, tunable types of circuits. We were able to receive funding from NASA that enabled us to really grow that capability within the lab. So we were able to look at design tunable LNAs. We were able to design and look at tunable filters, tunable power amplifiers as well. And then as we moved further on in 2014, we began now to look at gallium nitride and really began to look at how we can improve the power and efficiency as we moved higher in frequency. In 2017 is where we adopted the new name ARMED. And the reason why we adopted the new name ARMED is because it really best reflects what we do today as it relates, it best reflects what we do today regarding our capability in that we're a laboratory that supports centers. So we're a laboratory that works on different projects to support centers in the areas of microwave engineering and wireless communications. And then in 2018, we began to look at cyber and security issues. And so we started off with looking at IoT device identification and authentication issues. And then today, with the onset of 5G, we're now looking at growing our program to support 5G, to investigate issues, vulnerabilities, security issues, and just being able to model what's going on with the communication systems in 5G. So that's where our next step is moving towards in the future. So these are the resources that we have in ARMED. Currently, we have 2 associate professors. That includes myself and Dr. Dwayne Harvey. We have 5 doctorate of engineering students, all of whose research we're going to share with you today. We have 1 Master of Engineering student, and we have 5 senior capstone design students. I do want to make a note here that the graduate students, what we do at Morgan is the goal is to really align our student projects our student research, particularly at the graduate level. We try to align it and make connections with industry such that they're solving real problems. If you noticed in our mission statement, our mission was about doing applied research. The same thing with our capstone design students. Again, we try to make the alignment with industry and students so they get the mentorship from engineers, as well as they're working on realistic problems as well. The current capabilities that we have, you see these two folders here. We have capabilities to do RF device characterization. We're able to do circuit and subsystem design, advanced algorithm modeling and design, and we're able to do on-wafer probe measurement up to 140 gigahertz. Now, in areas where our measurement capabilities that we don't have, again, this is where our strategic partnerships come into play, where we establish MOUs, memorandums of understanding, with our partners to utilize their facilities to help fill in whatever measurement gaps that we may arise in our current lab. So as we look at the things and the capabilities that we have within the ARMED lab, one of the things that we wanted to, again, like I mentioned before, wanted to take a look at was wireless technology for future networks, which is 5G and beyond. As you know, the number of connections are increasing, the number of devices are increasing. You're going to have machine-to-machine, device-to-device types of communications. The idea that folks are demanding more information, more bandwidth, more speed. So all of these things is pushing the development of devices to operate in the higher frequency range, which we call the millimeter wave range. So in order to meet the demands, the higher frequency spectrum becomes very, very attractive. There's going to be a need for short range connectivity where you have these ultra small cells now, in which folks can support virtual reality types of applications, having additional indoor base stations, having spectrum sharing. So new components, new electronic circuits, new architecture designs are required for 5G and future wireless products at these millimeter wave frequencies. And this is where ARMED is positioning itself in order to be able to address some of those needs for 5G components and electronics. So if you notice here, there are two pictures here. On the left-hand side, you see a picture, that's a picture of inside of one of our Faraday cages. On the other side, you see a picture of our high frequency measurement laboratory. And as you can see, there are two students that are working in there. We do, as you see the list of hardware that we have, we're able to support measurement, like I mentioned, all the way up to 140 gigahertz. We also are able to do circuit simulation and optimization using the software tools that you see there below as well. So now what I want to do is I want to talk about some of the projects that we have been working on within the ARMED lab, where we think that some of these projects can help us to address some of the issues in 5G. And so one of the work that we have been working on are highly efficient SSPAs. The objective, of course, is to be able to improve the power amplifier power, linearity, and efficiency performance. But instead of using a spatial combination type of approach, we wanted to look at using the planar combination approach. And so we utilize a modified WIT coupler power combiner. We called it the WIT power combiner. The name stems from the name of the author who actually created the WIT coupler. And the reason why we're using this combiner is because it actually incorporated additional harmonic suppression within the coupler itself. We were able to benchmark the performance of the WIT coupler at S-band, and we did publish some work on that. And so we wanted to extend that capability and move it to see if we can get the same type of performance as we moved up in frequency. So the design that you see here was done at 26 gigahertz. It was done on gallium nitride, and we were able to achieve 2.4 watts of output power. You see the circuit schematic and the corresponding impedances of the WIT coupler in your lower left-hand corner. Some of the benefits of using this type of coupler is that we're able to have increased power density in fewer combining stages near Ka band frequencies because we're using gallium nitride. And we're able to suppress the second and third order harmonics to improve the efficiency performance. And because we have fewer combining stages, we're able to achieve lower losses in comparison to the traditional, like Wilkinson planar combining method. Now that design was at 26 gigahertz. We just again decided to look at designing this coupler at 120 20 gigahertz. And now this work was funded by NSF EARS, and this work was in collaboration with UC Berkeley, where the goal was to develop a power amplifier at this frequency that would be able to achieve higher power performance in comparison to the silicon-based CMOS front end that they were using at the time. For this particular work, we were able to optimize and lay out the coupler and obtain simulation results where we were able to show harmonic suppression at the second and the third harmonic frequency. Also, I do want to say that from this work, we were able to define an optimization method by which lengths and widths had particular impacts on the different harmonic performance. So this slide here is more of just a general slide to say, hey, our goal is, again, we're moving higher in frequency. Right now, we do have a doctoral student, Herman Cortez. He's looking at developing an abbreviated TR module in GaN at 130 gigahertz. So the things that we have been doing at 120 and at 26, we're going to be taking those lessons learned to help us to be able to apply it and do the design at 130 gigahertz. But as you all well know, when we consider issues at these frequencies, there are additional issues to consider. And so that's part of his research as it relates to looking at what those issues are. We're hoping to be able to submit a design for fabrication in 2021 and hopefully be able to test it late in 2022. Again, these types of activities are only possible through strategic relationships that we have with our collaborators and sponsors. As we're looking at working and optimizing device performance at these millimeter wave frequencies. One of the things that we ran into was errors in calibration, particularly at F-band. We currently have, as you saw in one of the pictures, we have a on-wafer probe station, which is a manual station, such that every time we do a contact on the wafer, when we raise the probe tips and when we put the probe tips back down, there are slight phase adjustments that are made because it's not an automatic system, it's a manual system. So we do the probe placement we do the probe placement visually. And so we realized that was contributing to errors in our calibration. And also because the probe tips are so close together, we also noticed that there were errors as it relates to crosstalk. And so I have two doctoral students who are looking at addressing these errors. One student is, we have been working with Keysight, and he's working at developing a process by which to be able to do a manual calibration that can be verified and repeatable. And the other graduate student is looking at how to model crosstalk and be able to de-embed out those errors from the when a calibration cycle is done. Our next project is about reconfigurable analog electronics. In this work, the goal is to provide advanced electronic technologies to enable tunable, reconfigurable communication systems to support dynamic spectrum allocation, multi-mode, and multifunction capabilities. For this particular work, Dr. Shani Kanti, she was working on the development of a self-structuring bandpass filter where we're able to adjust both the bandwidth and the center frequency of the particular filter. And so the idea here is that with the reconfigurable analog electronics, that helps to support spectrum-aware technology, where now we can be able to implement machine learning algorithms to control the frequency performance of tunable components. And the last project, which is a highly active project right now, surrounds IoT device identification using RF fingerprinting. The goal of this particular work is to develop a real-time monitoring system that uses physical layer characteristics to authenticate IoT devices that enter a network. And so if you look in the upper left-hand corner, you see the process by which that we use to capture the signals. We do signal processing, and then we go through a classification model in order to, using features, in order to help to generate the fingerprint, a unique fingerprint for a device. The idea is that by using RF fingerprinting, this is an approach at the physical layer that would support multi-factor identification for increased security within wireless networks. And just to share a little bit more about that, again, this particular work stems from the fact that, hey, humans have fingerprints, and these fingerprints are based upon distinct features that belong to each individual, and these features are difficult to replicate. And so what we're saying is that in this IoT space that each IoT device have a unique fingerprint. And we obtain this fingerprint by observing the RF emissions from the device. And these fingerprints are comprised of features. They're extracted from the signals that are distinct to a device due to the variations in the manufacturing process associated for that particular device. And so again, if you look at the key system components, the IoT device transmits the signal. We actually use a Tektronix receiver to capture the signal. We go through a process of processing the data to extract specific features. Currently, we've been extracting statistical features. The statistical features are based upon the variance, the skewness, and the kurtosis of the signal over a specific region of interest. And then we enter these features through a classifier, using a machine learning algorithm. And then we do the device classification to see whether or not the device is identified. Current approaches to RF fingerprinting. For most papers that are out there, folks are assuming that the features are the same across all the devices in the system, so they use the same features. Also, fingerprints are the same over time and do not account for environment changes. And then frameworks require modifications to be made to the IoT device or protocol for real implementation. So our work is to try to address some of these gaps and limitations, where in our work we have found that each device requires different sets of features by which these features are used to classify the device. Also, we are looking at the channel. We're looking at the RF environment, the spectrum environment, to see what are the things that are within the channel parameters to help us to identify things, not things, but to help us to identify devices within that network, to see if there is an illegitimate device or a legitimate device. We're trying to see if we can optimize or look at changes in the channel parameters as well, to see if there are things that we can use to help us to add to the fingerprint that we create for our devices. So in our feature generation, like I mentioned, these features include the amplitude, phase, and frequency of the kurtosis, skewness, and variance of the captured RF signal emissions. So we captured nine features, and we trained these features on 25 different classification models. And we tested the classification performance on a Samsung hub and a single lid light bulb. And so from these pictures, what you see are the results from the classification. As you can see for the Samsung hub, there is a distinctiveness in terms of boundaries to help to identify the hub. Where the hub is the dots in the orange, and if it's not the hub, it's the dots in the blue. And so as you can see, when we used all 9 features to help identify the device, we were able to see very clear boundaries. And when we went to 3 significant features, we were able to still see distinct boundaries. Now, what became very interesting is that when we used all of the 9 features to help to classify and help identify the device, we didn't get good success with the single lid bulb. However, when we used the 3 significant features to help with identification, you see here on the right-hand side that the orange dots that begin to cluster in a specific region, which emphasizes or shows that, hey, it's really beginning to identify the device based on these three significant features. So, so one of the things, like I mentioned, we were able to show that, hey, even though we trained the devices using these 9 features to help to identify the device, we saw that by using the most significant features would enable us to be able to identify specific devices. So that tells us that the same features may not be applicable to identifying all devices. Right now, we have submitted that work to be published. It's still pending. It's still under review at this time. So now I'm going to kind of change things a little bit here. And so I've given you the history of ARMED, where we started from, what we do, our capabilities, some of the work that we have going on in the lab by our students. Now I'm going to just touch on our student investment model. One of the things that we do really great is targeted recruitment, whether it's through outreach, undergraduate students. Because as faculty, we have intimate knowledge of the students, we work with them in our classes, we know the students that are able to be active in research while doing their undergraduate studies. We have found that when we're able to engage students at the undergraduate level in research, they're more successful academically, and also they're more successful when they go out on their internships and when they obtain their first jobs. And so this is our student investment model. The idea is to recruit students, retain them through specialized programming that includes the engagement with industry partners such as Tektronix, and then, of course, promote student achievement and success through graduation, such that industries like Tektronix will be infused with skilled talent at your organizations. So that pretty much concludes my talk today. Here are some selected references. Here is my our contact information, either myself or our ARM scientist, Dr. Dwayne Harvey, and if there are any questions.
Thank you, Dr. Kornegay. That was absolutely amazing. The technology you talked about was really exciting. So thank you for sharing all of that with us today. That was, yeah, very, very interesting. So, so far we have a comment from Chuck, and he points out it would be interesting to see how to track the RF fingerprint over time as the IoT device and components age. So to further the analogy, like your finger gets bigger or swells when wet.
Exactly. So, so even when your finger gets bigger or swells, there's still there's some permanence that's associated with the features that are used to define your fingerprint. And so what we're hoping to look for are those permanent features that, regardless of what happens to the channel over time, that we still would be able to identify the device. And that's one of the reasons why we wanted to start looking at the channel parameters to see if those parameters would give us insight as to helping us to identify things that would be that could help to serve as permanent features.
Are there any other questions for Dr. Kornegay? You can either unmute your mic and ask directly, or if you'd like to put it in the chat. Okay, we have another one from Gary. Have you published an article about the 26 gigahertz gallium nitride PA based on the WIT combiner?
Yes, and the reference is noted in the presentation, so I can copy it and put it in the chat for you. Yes.
Yeah, thank you, Gary. Gary is one of the co-founders of Microwave Journal, so thank you for participating and partnering with Tech.
We have another question from Keith, and he says, this is an amazing presentation. Can you comment on the personal accomplishment that you have experienced in training the next generation of technical leaders, being both female and persons of color?
Oh, that's a mouthful. So sometimes it's really hard to sell your accomplishments, so to speak. One of the things that I can share about the work that I've been doing is that someone taught me how to do it, and that was my advisor, Dr. Carl White. He was really successful in terms of inspiring and motivating students like myself to get into these highly technical areas. And he did it with just being himself and making it fun, making it relatable. And that is what I try to do with my students is, hey, I try to make it relatable. I try to provide them the support that they need. I'm not just a faculty member just out there on paper, but I'll get in the lab with them. I'll have those discussions with them. So it really does take an investment with our students, and it takes time. I've had students that have been met with different challenges, whether it's psychological challenges, personal challenges, social challenges. Those are the types of students that we're often met with. Sometimes they're low motivated, and so how do you get students who are low motivated? They come to college thinking that they're prepared, and then it's almost as if they get the rug swept out from underneath their feet. Who's there to help them to get a better sense of self, to revive their confidence? That is where we come into play. So my work, my day does not end at 5 o'clock. It does not end when the class ends. I'm always in conversation with the students, seeing what's going on with them. So part of this training is not only the technical training and the capabilities, because they can do it, they can learn. But part of it is also being met with the other social aspects and the personal aspects, those and professional anxieties. Those are the other aspects that we deal with to help train the next generation of technical leaders, whether they be female or persons of color, or whether they be disabled. Once students know that you care, it goes a very long way. And that's how we have been able, I've been able to get students. They got to know that you care about them, legitimately, that you care. And one thing that I do know about females is that females are very detailed oriented. They get easily discouraged, especially when things they don't get it, so to speak. And so one of the things is to, I remember Selu was talking about that, is to have that level of support. Hey, you may not get it like how X person over there gets it, but you do get it. And continue to encouraging our females to vocalize what they get versus what they don't get. I learned the most when I had problems. That's when I learned the most. So those are some of the things that I've experienced. in training the next generation of technical leaders.
Yeah, thank you, Dr. Kornegay. That was, yeah, that is a very powerful message that you talked about support and, you know, showing that you're there, and, you know, the teaching goes beyond the classroom. And I think when students know that professors care and are behind them, they're more likely to succeed and continue. And just as a side note, I'd like to point out that, you know, Dr. Kornegay, you know, the first meeting that we had last week, she tried to recruit me to become a PhD student as well. So her recruiting never stops, but she really believes in it. And so, yeah, thank you for what you do, Dr. Kornegay. It's really important work, and I'm sure your students really, really appreciate it. So we have a few more questions. Thank you, Dr. Kornegay. Amazing presentation. Any thoughts or ideas of taking this exciting technology and extending access and relatability to STEAM in underserved communities? Any pitfalls to avoid? And this is from Wilson Lee.
So any thoughts or ideas of taking this exciting technology and extend it? Yes. So being engaged, exposing it to them early and often. I remember as I was coming through high school and middle school, you know, I never saw a female engineer. I didn't know what that was. So exposing early and often, number one. Number two is, oh my goodness, the number two just left my head. But definitely exposing early and often, especially for females. They need to see role models. They need to see that connection, particularly in underserved communities. Any pitfalls to avoid? Yes, pitfalls would be any preconceived stereotypes or biases sometimes, and being aware that we all have conscious and unconscious biases, whether it's from just our environment, our interactions. We all have conscious and unconscious biases. And so it's important to be aware of that and be cognizant of that. I think sometimes looking through the other person's lens is helpful as well, so that you're more sensitive and aware of that person's possible experience, so that you can be able to make those connections better, so that you'd be able to recruit and to get that student. So when you talk about the underserved communities, the community or the population of students that we work with, they're relational. You have to have that relationship, and you have to find that commonality, that connection to make that work. And so definitely a pitfall to avoid would be the unconscious bias, because sometimes we don't even know that it's there until we said something or do something or don't act, or we respond in a certain manner in which it reveals itself. But that's definitely a pitfall to avoid.
Thank you. That was extremely insightful. And I think that's some of the things that, as part of Women in Technology, we're trying to do as well. And now that we're combining forces with BEM, I think we have an opportunity to work against any of those stereotypes, you know, unconscious biases, and kind of change the conversation at our level. We have another question from Sarah Bowen. Are you looking at free space optics in addition to RF communication? What applications do you see for optics versus RF comms in the future?
So right now, we are not looking at free space optics. However, I do know that the free space optics are being considered for very short wavelengths. Also, I believe in the backhaul, there are conversations where folks are looking at having hybrid systems, where you have the optics at one part and then you convert to the microwaves for the other part, or for a different frequency, depending upon the line of sight. So if you don't have good line of sight, then you switch over to the microwave spectrum. But if you have excellent line of sight, then you'd use the free space optics. So those are the types of conversations that I'm aware of, but we're not currently looking at free space optics within our lab.
Okay, thank you for that. I don't see any other questions. A lot of congratulations and thanks to you for sharing your thoughts. Okay, we have one more. What are the applications targeted for 6G?
So the applications targeted for 6G are like your smart cities, your smart industries, your virtual immersion, virtual reality immersion types of technologies, because those are the things that's really going to require the higher bandwidths. So those are the types of applications that I'm aware of that's targeted for 6G.
All right. Well, we are at the hour, and I do want to take this opportunity once again to thank you, Dr. Kornegay, for taking the time to be with us today to talk about Morgan State University and share your research and your great program that you have for your students. It was very enlightening for me. I learned a lot, and I hope it's the same for all of our attendees today. So thank you all for attending this great talk, and we'll look forward to seeing you at our next Women in Technology event.
Thank you very much.
Thank you for having me.
Thanks.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks much. Bye.
Thank
Yeah,
you.
very good. Thank you.
Thank you.